Okay, so hopefully you found C sub P for nitrogen gas in table A2B. You don't have a row for 291 Kelvin. You have a row for 250 and you have a row for 300. But for nitrogen gas, there's no change in C sub P between those two. It's 1.039 kilojoules per kilogram Kelvin, all the way from 250 to 300 Kelvin. That C sub P works there. Yeah. Okay. I gotta reset my timer. I forgot to start it. I apologize. Okay. Yeah, that's gonna get me. I had to clock my timer back just a little bit. Alright, what the heck are we trying to do? We're trying to find the speed. We've solved for speed. The only thing we need to know is C sub P average. We've got that now. Okay, V2. Let's get down to some calculations. V2 is equal to square root of 2 times quantity, 1.039 kilojoules per kilogram Kelvin, multiplied by, what do we got here? T1 is 7, T2 is 22, and those are Kelvin. Steve, wait, those are Celsius. Yes, a change in Kelvin is the same as a change in Celsius. And if you don't believe me, feel free to go ahead and convert both these to Kelvins and then take the difference, and you'll get to the same conclusion, okay? And a change in Celsius is okay to not convert. When we plug those values into ideal gas law, we will need to convert those, okay, if we do that later. I think we do. Okay, so that quantifies this. I'm going to add that to this kinetic energy term. Now, let's look at our units, though. I've got kilojoules per kilogram here. What units, so the important question here is, what units would you like? Because this is going to be in meters per second, and it's going to get squared. So this second term is going to be meters squared per second squared, and this is not meters squared per second squared. At least it doesn't look like it. So what units would I like? Well, I'd like V2 to be in meters per second. That's always, when you're not sure about your units, ask, what units would you like? I would like meters per second here, please. Okay? So how do I get there? I need meters squared per second squared underneath the square root. So I've got to get kilojoules per kilogram to meters squared per second squared. How do we do that? Well, if you go over kind of to the side, so somewhere over to the side, right, to the side. If I'm in the classroom, I just go to the far end of the chalkboard or the whiteboard and I do this. But I don't have the room here, so we'll just work right here. A joule, what does a joule break down into? What does a joule measure? A joule measures energy. Okay, so energy is force times distance. In the SI system, a joule is a Newton meter. So I don't have to memorize a joule as a Newton meter. You can if you like. If you'll memorize this as energy, and energy is force times distance, then the units kind of are a little easier to try to remember. So a joule breaks down into a Newton meter. What does a Newton break down into? Well, this is force. Force is mass times acceleration. So this is kilogram meter per second squared. That's a Newton times a meter. So notice that a joule is a kilogram meter squared per second squared, or a joule per kilogram is a meter squared per second squared. This is not a joule per kilogram, this is a kilojoule per kilogram. This is a kilojoule per kilogram. So to convert that, there's 1,000 meters squared per second squared, because there's 1,000 joules per kilogram for every kilojoule per kilogram. The common error here is just to assume the units are going to work out. And as I mentioned on the exam 1 solutions, we're not scientists and we're not mathematicians. We don't get to just blindly assume the units work out. We've got to make sure. Otherwise, we kill people, or we crash equipment, or we tear things up and we get sued. Bad things happen when engineers ignore units. So if you want to survive engineering school, you can't just ignore the units. We've got to make sure the units work out. Okay? So even in the SI system, they don't always work. So in this case, the big giveaway is if you're dealing with magnitudes. Right? Here I've got kilo, right? And so that when I convert that to base units, it just doesn't work. So I've got a factor of 1,000 here, conversion factor. Okay. What the heck are we trying to do? Oh yeah, we're looking for V2, so I've quantified this. Now I need to add this in here. This is 200 meters per second. That's the initial kinetic energy. That gets 200 meters per second gets squared and divided by 2. That gives me the initial kinetic energy. And that should work. Okay. Make sure I don't have a glare on this. If I set that down, do I have a glare? No glare. Good. Okay. So, all right. Let's move it down here. That appears to be on your screen. Okay. So I'm going to take, let's see, what's my most complex thing? 7 minus 22 multiplied by 1,000 multiplied by 1.039. Okay. Add to that, so this, I'm going to put brackets because everything gets multiplied by 2. So add to that, I'm hoping I've got, this is right here, add to that 200 squared divided by 2. Perfect. So I'm going to multiply that whole thing by 2 and take the square root of the whole thing. And I'm getting about 94. V2 is about 93.97. You could say 94 and it wouldn't hurt my feelings. Meters per second. Okay? Alright. Let's look here and see how we did. I think I've got solutions in the notes. So let's, oh, actually, before we look at the solutions, how do we find the ratio of areas? Because that's the other thing I've asked for. How do I find the ratio of areas? Well, remember, we said this expression here. Also, the ratio of areas, A1 to A2, is equal to, we can solve this for A1 over A2, right? So A1 over A2 is going to be, what do we got? Little v1 over little v2 times big V2 over big V1. Okay? Solving this expression for the ratio of areas. Now, how do I find these specific volumes? Well, these are properties. What is my substance? How do you find properties? Well, you need to know what is your substance. I've got an ideal gas. Okay? So, I need to find properties of an ideal gas. Well, how do I do that? Well, I could possibly use ideal gas law. I could say P1 V1 is equal to RT1. And I could say P2 V2 is equal to RT2. And I don't need to know these volumes. I can find them. I know both pressures and I know both temperatures, and I can go look up the R value. I could find them. But I don't necessarily need them because all I need is the ratio of specific volumes. You have algebra skills, you're welcome to use them. Right? So what am I saying here? If I say, well, P1 V1 over T1 is equal to R, and that's equal to P2 V2 over T2. I could probably do this in my head, but that's where I'll mess up. So I can look at this and solve it from there. So let's see. This is going to be T1 over T2 times P2 over P1, I believe. Okay, so if we assume that's correct, that means the ratio of these is equal to, we said T1 is 7 Celsius, so that is 280 kelvins, right? Add 273. Don't just plug in Celsius values here. When in doubt, use kelvins. If you're multiplying or dividing, use kelvins. If it's a difference, Celsius is okay. 22, add 273 makes 295. 295 kelvins. And multiply by the ratio of pressures. P2 is 85 kilopascals. And P1 is 60 kilopascals. So this ratio you can compute 280 to multiply by 85, divide by 295, and then divide by 60. Getting 1.34. 1.345 or something. Okay? Alright. I know both speeds now. I know the ratio of specific volumes. I can solve for the area. Okay? Alright, so this is a solvable quantity. This is equal to 1.345 multiplied by 93.97 and divided by the initial 200. So I'm getting 0.632 here. Again, plugging this in here, this in here, this in here, and V1 over there. There we are. Okay, so I've got two answers. Fairly straightforward way to look at them. Let's look at the solutions. I've got, I think, just enough time. Yeah, I got about 3 minutes here. Just enough time to look through the solutions. Okay, so this one said, you know what? We've got table properties for those H values. And so they went and looked up the table properties. This solution set looked up the table properties. It said H1. Now, for the nitrogen, oxygen, carbon monoxide, carbon dioxide tables, these are per kilomole, not per kilogram. So you're going to have to go look up the molecular mass to find, to convert this to kilogram basis. Okay? So this one did this a little bit differently. This one used table properties, and that's okay. Notice you do have to interpolate. You don't have a row for 295 Kelvin in your tables. If you look, you don't have a row for 295 Kelvin, so they had to interpolate that one. Okay? For the calculations. Right? So it looks like this. Similar to what we had. Right? Here's how they're quantifying their delta H. Okay? Kinetic energy. Solve for V2. Solve it down. They're getting about 93 meters per second. We got right around 94. So honestly, this is okay. You're not going to get exactly the same using, because we use C sub P. Right? Here they just looked up H values, and they had to interpolate the second one at 295. And that's okay. Nothing wrong with that. Okay? And they also had to divide by the molecular mass to make the units work. Or you can do it the way we did it. And say, well, you could also use C sub P at the average temperature. They found, just like we did, that's 1.039. Run this through. Looks like very much like our same expression here. Right? We've just solved it. They didn't solve it, but they said, you know what, the answer is about 94 meters per second. So far, so good. Okay, so again, either way is fine. Which way is right? They're both right. I would count both of them 100% correct if you get a good C sub P average value. Right? You have to get a good C sub P average value. This one will do just as well as the table properties will. Also asked to find the ratio of areas. Right? So algebra, they found the specific volume ratio, same as we did. Okay? And they got pretty close to what we did. Looks like, yeah, they were using 93 meters per second. We used 94 for V2. So they got really close. I would count either of these correct. I wouldn't count either of those wrong. Okay? Alright, if you have questions, ask them in the comments, send me an email. I've got a heat exchanger problem we can look at next. But this ought to get us going. Okay? So we'll pick up a heat exchanger for lecture 12 here. So take your break if you haven't taken a break yet. This is normally where, if I'm working these in class, I would give a break to my class. Say go use the restroom, get you some caffeine. If you drink caffeine, or do whatever you have to do to take a break. Don't take too long a break. In class, we'd start right back up in 15 minutes. If you take you a couple hour break, maybe you don't come back good and strong. Take it just a few minute break. Do what you got to do. Come back as quick as you're ready. Okay? See you guys in a second.